So continuing on with the previous section, we want to start looking at things like, say, x squared equals 4y. That's going to define a nice equation, or a nice graph rather, in Cartesian coordinates, the rectangular coordinate system. It's not that hard to draw. And we certainly could, if we wanted to, change this into polar coordinates. Now, for a polar coordinate, we're usually looking at r equals some function involving theta. It's most of the ones we want to work on. It's not necessarily the only way to do it, but that's kind of what we like to go with. So we know that x equals r cosine theta, and y equals r sine theta. So from that, I've got r squared cosine squared theta equals 4r sine theta. So I end up with, if I divide both sides by r cosine squared theta, I'm left with r equals 4 sine theta over cosine squared theta, 4 tangent theta, secant theta, if I rewrite those in terms of trig functions without a quotient. So, again, not too tough, but for something like this, and it's almost kind of hard to see the point, right? If I looked back at this original equation, I could write this as y equals x squared over 4. I know how to graph that. That's not a big deal. But let's look at a few of these other ones that are given in polar coordinates and see what would happen if we tried to convert them back to rectangular. So if I wanted to try just r equals 5 secant theta, well, that's going to be the same thing as 5 over cosine theta. Now if I multiply both sides through by the cosine, I get r cosine theta equals 5. Well, and r cosine theta is something that I know, right? That can be converted into just x. This converts into x equal 5. And that's a graph we actually know. That's just a vertical line. So it's kind of interesting. That's what a vertical line looks like in polar coordinates. What if we had, instead of that, r equals 2 sine theta? Now if I want to try to convert this into rectangular coordinates, I don't have something to go on right away, because I don't have an r sine theta or an r cosine theta. So I'm going to use the fact that r squared equals x squared plus y squared, and I'm going to try to get an r sine theta in here. To do that, I'm going to multiply both sides by r. So I'm going to get r squared equals 2r sine theta. R sine theta I can replace with y, and r squared becomes x squared plus y squared. So I'm left with x squared plus y squared equals 2y. X squared plus y squared minus 2y is equal to 0. And if you go ahead and complete the square, for y, what you end up with is x squared plus y minus 1 squared equals positive 1. Now this should look familiar. You've got an x squared term, you've got a y minus 1 squared. This is a circle of radius 1, because we get that 1 over there. And the center is at 0, 1. This y minus 1 shifted the center of the circle vertically. Now that's something that we could graph with Cartesian coordinates, but we did need an x squared, we needed a y squared, we needed some completion of the square. 2 sine theta. That was about it. That was all we really needed. Now, I've got one other one for you. Let's try r equals 2 plus 2 cosine theta. Now if I'm going to convert this, I think I'll probably start the same place I did last time. If I multiply both sides through by r, I'll get an r squared, I'll get an r cosine theta. So r squared equals 2r plus 2r cosine theta. So I've got a few substitutions I can make. I get x squared plus y squared equals 2r plus 2x. But I've still got this pesky r in here. I want it just in terms of x and y if I'm looking to get it rectangular. Well, let's see what we can do about that. If I take x squared plus y squared minus 2x equal to 2r, well, I'm getting there. But I would still like to turn this into an r squared, so I can turn it into x squared plus y squared. Now I could multiply both sides through by r, which is what I did up here. The issue with that, I don't have any cosines or sines over here. So that would just introduce another r into the problem. I'd have a harder time getting rid of it. So instead I think I will just take this side and square them both. Squared plus y squared minus 2x squared equals 2r squared. Put that in parentheses so I don't lose anything there. And so I'm left with x squared plus y squared minus 2x squared equals 4r squared, which is really 4x squared plus y squared. So you can take out that bit in the middle, just have these two things equal to each other. Now I could multiply that all out, I could square it out, but that right there, that's pretty nasty. I'm not going to be able to explicitly solve for y in terms of x. I'm going to have a pretty hard time actually getting a sketch of that. And that seems pretty reasonable. If I actually looked at this thing and I tried to draw it in Cartesian coordinates, we'll cover more about how this comes about in the next section. That's what the graph actually looks like. And all of that came from r equals 2 plus 2 cosine theta. Much better than trying to get this graph by going with this guy. Good luck finding ordered pairs that make that guy true. It's going to be a big pain. So we're starting to see some situations where polar coordinates are really useful to us. In the next section, we'll cover some more about polar graphs.